Good day, class. In this lesson, we will learn to solve equations using DeMoivre's theorem. We will find complex number solutions to a polynomial equation. Let's check out this polynomial equation. We have x cubed minus 64 equals 0. We're pretty familiar with it at this point. We can isolate the variable x by getting the constant on the other side of the equation, and then we can take the cube root of both sides of that equation and identify the unknown value of x as 4. And if we substitute that back into the original equation, we will get a true statement. 4 cubed minus 64 gives us 0. However, we recognize right away that this is only yielding a single solution, whereas we're expecting 3 solutions. So let's tackle this by relating complex numbers to the field of trigonometry. So thinking about complex numbers, or looking at complex numbers in trigonometry, maybe I should say, let's start with the Pythagorean theorem, which at this stage in your practice is very familiar. If we're dealing with the Pythagorean theorem, we're thinking about the radius here of or we're thinking of a side A, a side B, and a side C of a triangle. And so we know this relationship exists where side C squared has the same value of side A squared plus side B squared. Well, it's also true that if we're thinking of this side C in terms of a radius, which we've done that in this course where in this field of study known as trigonometry, then we can identify a radius measure as well, and we see that relationship still holds true where r squared, or the radius squared, is equal to side A squared plus side B squared. And we can rearrange that conveniently to have the measure of r, have the measure of the radius anytime we need it in the field of trigonometry. Also, we can identify an angle measure. Again, at this stage in our study, we recognize that theta measure can be defined in terms of a tangent. So if I'm looking for that theta measure, then I have my opposite side and my adjacent side that I can relate to describe the measure of the theta. And I can do that using a calculator, or I can do that using a trigonometric, a unit circle, as our two most common forms to identify the measure of theta. Now, notice here, I want to plot a complex number in a plus bi form. Recall complex numbers being plotted in a plus bi form on the Cartesian coordinate plane. Notice how here I have 4 plus 0i. Look at what's happening here. That 4 is sort of on the real axis. We just take 4 steps over what we commonly know as the x-axis, and then it's almost like that imaginary axis being the y-axis, and we take 0 steps. So we sort of see where we land on the positive x-axis here. And then we do this again, and we can see where we land here in this example where we have negative 4 plus 0i. This is a complex number written in complex number form, and so we see that on what would have normally been the x-axis is actually the real number axis. The real part of that number, as every complex number has a real part and an imaginary part. And then on the imaginary axis, we're taking 0 steps. Look at these two examples, which are very similar. We're looking at 0 steps on the real axis, 4 steps on the imaginary axis. Very simple to plot complex numbers. We can compare these various examples and really get a sense of the relationship, sort of dealing with the Cartesian coordinate plane, dealing with a real axis and an imaginary axis versus an x-axis and a y-axis. Now, with that being said, let's sort of put our heads back in the space of solving this equation. Where are our other 2 solutions? Well, DeMoivre's theorem to find complex solutions to a polynomial equation sort of gives us a formula. So this French mathematician has developed and proven that this formula will identify all the complex solutions to the equation, such as the equation we're given. So notice how we're calling that solution by a z. It's sort of an imaginary ways to describe a location in space on that imaginary axis when we're involving an imaginary axis. So we're dealing here with z sub k. I'll talk about what that k is. Really, I refer to them often as iterations, but that has a value equal to our n. Our n sort of describes our number, if you will, of iterations. And so we have our r, that represents our radius, as we talked about in the previous slide. And so we need to know that r measure. We need to calculate it. Also, we see we're going to need the theta. The theta is another measure by which we'll calculate. And our n is going to come from the power of our polynomial. Here we have x to the third power. So that n is not difficult to find. The r, we're going to calculate that. And the theta, we're going to calculate that too. And then our k is going to describe our number of iterations. So let's take a look at what I mean by all of this. Here we have the formula. And let's apply it. But first we need those measures. We need to identify the radius. We can see here that since x cubed equals 64, then our number to the right of our equal sign is going to be in a plus bi form. Our a measure is going to be 64, and our b measure is going to be 0. And so we apply that to our formula to find the radius, and we discovered that the radius for this particular equation is going to be r equals 64. Here we can also identify, using our measure of a and our measure of b, the tangent of theta, or theta itself. And so here we discover, by applying the tools to solve this equation, tangent of theta equals 0 divided by 64, that theta has to be 0 degrees. Notice I'm choosing 0 degrees versus 180 degrees because my point is plotted in a plus bi form. And so I know with a plus bi being 64, then this is going to plot on the positive x-axis. So I'm going to choose the angle measure 0 as opposed to the angle measure pi, or as opposed in degrees, the angle measure 180 degrees. So let's take our givens. We have r is 64, theta is 0 degrees, n is 3, given as a part of the original equation where x is raised to the third power, and our k is the number of iterations. We're going to do 3 of them, which we're starting at 0, so 0 revolutions, if you will, around the unit circle. And so we're looking at k as 0, k as 1, and k as 2. And that will give us our power of 3 iterations here. Let's go ahead and apply this formula for the 0th iteration, the first iteration, and the second iteration. And so I'll substitute the given values that we have here, and then I'll just simplify. I can see that the measure or the value here is going to be my complex number solution. That will make a true statement in my original equation. If I were to substitute that number back into my original equation, I will get a true statement. The same will happen here. If I were to apply the givens, simplify, substitute that number back into the original equation, I will have finally my second solution to this polynomial equation. And then lastly, my third iteration here, I will substitute, simplify, and have my third solution to the polynomial equation.